So I think we should begin. So before I resume talking about the Feynman propagator, I think I should discuss briefly a problem that you would solve in the homework related to cosmology, just in case it's not clear what to do there. Okay, so the key thing to remember is that so the motivation is the following. So in a very early universe, it's believed, although it's not an established fact yet, but we're still accumulating evidence before we can be sure to say that it really happened. But there is a hypothetical era or hypothetical phase of the early universe where many theoretical physicists believe the universe went through an exponential expansion. So it expanded exponentially quickly. And this is called inflation, right? And so why this is potentially important is because inflation supposedly solves, there's some dispute about this, but supposedly solves some of the cosmological puzzles that we seem to see. So for example, if you look at the cosmic microwave background, what's the microwave background? It's the leftover radiation that was left over from the Big Bang, essentially. And it turns out that if you look at the sky in different directions, they all look like they have the same temperature. The cosmic microwave background photons have the same temperature no matter where you look. They have the same temperature to 1 part in 10 to the 5, roughly. So very, very close in temperature. And if you start thinking a little bit about why that might be the case, you might think, okay, there must be some mechanism in the early universe that makes sure that everybody was in thermal equilibrium with each other. But if you know some cosmology and you do a bit of calculations, you realize that just from the causality of it, it's in fact impossible. It's impossible that all of these photons were somehow causally connected to each other. So for one thing, it's easy to see, in fact, if you just know some relativity, right? The fact that the photons are just reaching you means that they, from opposite sides of the sky, they have just enough time since the beginning of the universe to hit each other. So how can it be that from opposite sides of the sky, they could even be at the same temperature? Right? So this is a puzzle, and so one of the ways that people have devised to solve this so-called puzzle is inflation. Inflation is, in fact, the hypothesis that the universe went through, the universe started off exponentially, but because the universe went through an exponential phase of expansion, it now looks acausally connected, right? So this is one reason why people are interested in inflation. The other reason is that it could potentially explain why we exist, basically, why the structure. So that sounds very grandiose, but what really is saying is that how the structure formed, right? We need how the structure formed. We need gravitational inhomogeneities in the very early universe. We need things to be a little bit more dense in some places and less dense in other places. And the reason for that is so that matter can start collapsing together, and with the collapse of matter, that's how you can form galaxies and stars and stuff like that. And then with stars, you can form also solar systems and so on. So that was really the beginning. And so what you're going to do in your homework is actually to do the first calculation, the first step of the calculation, that not the exponential expansion part, but the quantum fluctuations part. So the exponential expansion is actually described by the following geometry, right? So the coordinates I gave you guys is what's called the flat slicing coordinates in de Sitter space. So it doesn't look like exponential expansion, but so let me just write it in parentheses. But if you convert this coordinate system to what's called the observer coordinates, you will discover that this metric looks like e to the 2ht dx squared. Okay, so this is exponential expansion. Of space, right? So this used to be space. In flat space, then this would just be 1. But this scale factor tells you that space itself is expanding at an exponential rate. But this coordinate system is easier to do calculations in. And so what you're going to do is you're going to quantize a field, a massless scalar field. So you'll basically end up solving this guy as the Heisenberg equations of motion for phi. Okay? And so you know how it goes. In Minkowski space, what we do is we end up doing a Fourier transform. So in the cosmological case, you can still do a Fourier transform, but the time part of this is not clear. Right? So what you discover is that you can still split this guy up. So you just need to do it in 4 dimensions. So you still can do it in Fourier modes. And remember, in Minkowski, what happens is that the corresponding scalar field will look like this, right? It will look like d3k over the pi cube. And then what you want to impose is 1 over square root to k. And then what you have over here is that you have a of k, and then this guy will be e to the minus I k dot x, and then you add Hermitian conjugate. Okay, and so what's important here is that these are the mode functions. These solve the homogeneous equation. But there is a choice that you're making here. The choice you're making here is that the time I dt of this guy gives you a positive energy. In this case, you can see this gives you k0, which is actually, in this case, k, the magnitude, because it's a massless scalar. right? So the energy is just the momentum, the magnitude of the momentum. So likewise, there's a similar situation here as well, which is that you also have A, K, and then you need to now, instead of doing this, now the situation is just a little bit more complicated. You would have a function of time. Let me just, I call it F in my notes, so let me do something else. That means you would have something that is an exponential in space, but this guy here would be a bit more complicated as a function of time, right? So let me just call it, let me call it phi of t, phi of t, phi tilde of t, of eta actually, because it depends on eta, plus Hermitian conjugate. Okay? So the things you need to check are the following: that you know the equations of motion, so you also know what the Lagrangian is, so you can impose. So there are two things that you need to do based on your understanding of the Minkowski solution. Firstly, you need to impose or check that the equal time commutation relations holds, meaning the analog of x comma p equals to I, that needs to hold. So what you discover is that that tells you something about the commutation relation between A and A dagger. Remember that in this flat case, all you need to do is just make sure that A comma A dagger is delta function in K. Something like that will hold as well here, but because the mode functions here are non-trivial, you will also discover something about the Wronskian of these guys. So you will discover that AK prime dagger is it will be proportional to delta K minus K prime, but you will discover what this is. And then you will also discover something about the Wronskian of the solutions. Okay, these mode solutions, mode function solutions. That's the first thing, okay? And then I gave you the clue, another clue, and this is where the physics, an important physics lies, which is that in the Minkowski case, there wasn't a lot of ambiguity. When we choose this, we appeal to the harmonic oscillator problem, and this came out to be such that what I just said, which is that the time derivative is kind of like basically telling you that this is a positive energy solution to your Schrodinger equation, right? Because when you take the time derivative, it gives you the positive energy. Okay, so this guy in particular is the positive energy solution. I'll have more to say about it when we get the fermions, probably by the end of the week or maybe next week. But what you want to do in cosmology is you'll be able to find the solution of this guy, and you'll find that when you can arrange it in such a way where when you take the Hermitian conjugate, these two guys will be linearly independent. But you want to choose what I ask you guys to do is to choose phi tilde of eta such that, and I should say, in this coordinate system, t runs over the real line. But in this coordinate system, eta only runs from minus infinity to 0. Right? It can't run. So minus infinity is the infinite past, and 0 is basically the infinite future. And what you want to do is you want to choose phi tilde such that it approaches the Minkowski solution. or I should say e to the minus I eta in the infinite paths. Okay. That's a choice that we make. And this choice, I want to emphasize, this choice corresponds to a choice of vacuum. Which is a subtle point. So this is not a class on quantum field theory in curved space-time, but I just want to give you the gist of how to solve this problem and let you think about it on your own a little bit. Right? So all you need to do is you need to solve these mode functions. You need to figure out the right commutation relations between A and A dagger. That will also tell you how to normalize these states. If you are in doubt, just look at the way we normalize the Minkowski case. You will also find that there's actually a Wronskian here that you need to normalize properly. But this guy, you will discover what is the right choice of normalization. And furthermore, you want to choose psi tilde so that in the infinite paths, you basically get a solution that looks like Minkowski space, right? And so, by the way, that's called a Bunch-Davis vacuum. But at least within this Bunch-Davis vacuum, you can then go ahead and calculate the following. You can then go ahead and calculate the vacuum expectation value of the two-point function, but in Fourier space. So you can go ahead and calculate this guy here, eta of k, and then phi tilde eta of k prime. And the physics is the following. The physics is that as eta goes to minus infinity, this tells you the variance, right? This is a two-point function, so you should think about it like in a statistical sense, except that it's not really statistical uncertainty that we're calculating here, but quantum mechanical uncertainty, right? This is quantum mechanical variance. Two-point function in statistics is the variance of the statistical distribution. But here, the distribution, the randomness comes from not statistical uncertainty, but quantum uncertainty. But essentially, the interpretation is very similar. And what you're computing here is basically what is the variance of this quantum fluctuation in a very early universe. And this variance is precisely the object that is responsible for generating inhomogeneities in the early universe, which I just explained, is what also gives rise to all the structure that we see around us, right? If inflation is correct, we're not 100% sure yet, but if it is correct, there's still some dispute about that. Some people don't strongly disagree with inflation, so the jury is still out. But if it is correct, then this two-point fluctuation is in fact telling us why we exist, to put it simply. So this is why I give the homework, to show you that what you have learned so far is already enough. You need to do some work, but it is basically enough to let you understand something about how quantum fluctuations work, even in the cosmological context. Okay. Okay. Anyway, come and talk to me if you have some trouble with this. I probably should give more hints in the problem. So I might add, if you have trouble, look at my notes. Okay, I might give more hints just to make sure that you guys don't get stuck Or just look at a cosmology book. Actually, the answer is in the cosmology book. So, but I want you guys to look through it yourself, because it is just very, very similar to the quantization procedure that we went through for the scalar field in Minkowski. Right? The only thing you need to do is you need to solve an ordinary differential equation. Actually, I should just tell you, it gives you a bunch of either Hankel or Bessel functions. Right? So depending on what basis you choose, it's a bunch of Hankel functions. But you have to choose the right set of Hankel functions to match this Bunch-Davis, this choice of Bunch-Davis vacuum. So that's the answer for you, basically. But you should work it out for yourself and see how it works, how to do it. The other thing about quantum fluctuations or quantum field theory in expanding universe is that because the background is time dependent, the Hamiltonian is time dependent. And so what these fluctuations are telling you is that actually there are particles that are being produced from the vacuum. Yeah, I really shouldn't be using the blue marker. Yeah, anyway, so so this is something that is important is also a physical point worthy to remember, which is that if your Hamiltonian is not time independent, then it in fact doesn't commute with itself at different times. And if it doesn't commute with itself at different times, most of the time it will also not commute with a number operator at different times. So because the number operators we've just seen is just A dagger A of each mode. But if that guy comes from the Hamiltonian, and the Hamiltonian is time dependent, then it will not, in fact, in general, commute with itself at different times. And what does that mean? It means that, in fact, particle number is not conserved, is not constant in a non-equilibrium situation, where in a situation where the Hamiltonian does depend, is in fact time dependent. You will discover that particles can be spontaneously generated out of the vacuum just by virtue of being in a non-equilibrium or in a dynamical situation. And cosmology is in fact a big example of that. Right? So particles are produced just, they're basically popping out of the vacuum for free. So that's something important to note as well. Okay, so let's come back now to the Feynman discussion of the Feynman-Green's function. So our strategy is as follows. Okay, so what we have done was to define first the Feynman-Green's function as the following Fourier representation. Okay, and what we so what I'm going to do is I'm going to evaluate this integral up to a point where it's going to be useful for us. And then after that, I'm going to show you how this object will come out of a similar two-point function calculation, right? So this was cosmology, but now let's come back to Minkowski space, and we'll discover that this guy, in fact, comes out of, so let me just write down. So we'll discover that this, in fact, is the vacuum activation value of the time-ordered product of phi of x and phi of x prime. So sometimes I'll write vacuum, sometimes I'll write omega. So Pascal encoder uses omega. Actually, in this case, I'll write it as 0 because this is a non-interacting. Vacuum, meaning for a linear theory, right? If it's a non-linear theory, then we will use omega, right? So this is the interacting or non-linear theory vacuum. This is not that, right? So I want to emphasize that the interacting case is very complicated, and in fact, we will also discuss how we calculate it perturbatively. Okay? But one step at a time. So we're going to first tackle this guy here, and then I will talk about the non-linear case. So let me erase this one. And let me just put down 0. Okay. Different color. Let's see. Okay. So like I told you before, the thing to know about k squared minus m squared plus I epsilon is to see firstly that this factorizes into k0. So epsilon, remember, is just an infinitesimal positive number, right? And actually it has lots of dimensions of k squared, otherwise it won't make sense. So what you can do is you can view this as basically, let's see, so it will basically be k and then minus I, let's call it epsilon prime, and then minus E, k, and then let's see whether this works. Okay, and then k0 minus or plus I epsilon plus E. Okay. Okay, so let's see whether that works. Okay, so let me not put it. So this is actually equals to k squared. K0 squared minus the square of E plus I epsilon squared, right? And let's see whether this works. I'm going to ignore, because epsilon is very small, so I'm going to ignore, yeah, so I think it's wrong. So it's plus and minus, right? So this will be minus. And then I think it's good. Okay, yeah. So this will be k squared, k0 squared minus E squared, and then it will be plus 2I epsilon prime E, right? And this is in fact, I'm going to just relabel it as epsilon. Yeah, so why is this important is because if you write it this way, sorry, I keep forgetting my primes. So epsilon prime, by the time you get here, epsilon prime E, 2 epsilon prime E, you now relabel it as epsilon. Okay? And now why is this important? Because this tells you that this tells you I don't like markers. That's what it tells you. So K0 on the K0 plane, on the K0 complex plane, this is in the denominator. So when you set things to 0, let's look at what this guy does, right? So what this guy does is that it tells you that K0, this is 0 when K0 equals to E minus I epsilon prime. right? So where is minus I epsilon prime? It means it's somewhere here. And then this factor, when this is 0, tells you that it's when k0 equals to minus E but plus I epsilon prime, which is somewhere here. Okay? So when you do the integral over k0, what it's saying is basically skirt this pole by going under it. And this minus I epsilon prime tells you to skirt this pole by going above it. Right? That's basically why we choose an I epsilon. You can either think about the pole being displayed slightly upwards here and slightly downwards here, which is why I have to be very careful about what the sign of this guy is. Or I can think of the poles as this one at minus E, but I'm told to go under it, and then the pole over here is plus E, but I'm told to go above it, right? And many books will just tell you to slant, just take the straight line and just tilt it slightly, right? I mean, they're all saying the same thing, but basically take the poles in that particular way. And so now let's figure out what does it actually mean for the contour integration, right? So let's focus on the k0 integration. So dk0 over 2 pi e to the minus I k0 of t minus t prime over k squared minus m squared plus I epsilon. Okay? And so let's remind ourselves that this is in fact just k0 minus E, k0 plus E, but now with the Feynman contour, which is exactly this whole I epsilon business over here. So as usual, what we're going to do is we're going to consider the case, what happens when t is greater than t prime. So remember, this step function tells you that it's 1 when t is greater than t prime, is 0 when t is less than t prime. So this is just saying, the presence of this is just telling you, consider the case when t is greater than t prime. So when t is greater than t prime, let's see what happens. Okay, so remember that on the complex, the way I like to remember is that let's just consider going either this way or this way, because we're about to close the contour either this way or close the contour this way. Okay, so if you remember that it is minus I over here, then evaluating it on the infinite imaginary line will be either plus or minus I infinity times t minus t prime. So this will give you e to the minus I times I gives you 1. So this will be plus or minus infinity times t minus t prime. So this is how I like to remember it. If t minus t prime is positive, as is the case here, that means we want to choose the negative sign, so that the contribution when we close the contour should be exactly 0, right? But if it is plus infinity, then surely that contribution is not 0. In fact, it's infinite. So minus sign here means we should therefore go this way, right? So when t is greater than t prime, close this way in that lower imaginary plane. When t is less than t prime, then this guy is negative. And so we actually want to choose the positive sign, which means close the contour by going this way. Okay. Any questions for me? Are you guys all familiar with contour integration? Yeah? Okay. Okay, so let's now do this. Okay. So again, 0 indicates it's the non-interacting vacuum that we care about. And we're going to time order it. So time order, remember, means the following. Basically, you have the two situations when the time of x, which we call t, is bigger than t prime, the time of x prime, then we let phi x tend to the left of phi of x prime. And then it's the other way around, meaning if t prime is greater than t, then we let phi of x tend to the left of, I'm sorry, the other way around, phi of x prime is tend to the left of phi of x. And then we're going to calculate the vacuum expectation value. So what that means is basically, let's just calculate one of them, right? Because these x and x prime are arbitrary anyway. So once we have one of them, then we can just swap the symbols. So let's calculate this guy, which is, by the way, called the Whiteman function. So once you have the Whiteman function, then you can get the time-ordered guy very easily, right? So let's do that. So what we're going to do is we're going to use the mode expansion, and these guys are expressible through their Fourier Transform, right? So I'm going to have a k, and I'm also going to get a k prime, k for the x, phi of x, and k prime for the phi of x prime, okay? And so we'll have the vacuum, and then let's write down phi of x first. Phi of x will give you, actually let me also write out, let me pull out the 1 over, remember there's always a 1 over square root 2 ek, and there's a 1 over square root 2 ek prime, okay, for the mode expansions. And then we do vacuum, and then phi of x will give you ak e to the minus ik dot x plus ak prime, ak dagger, I'm sorry, and then e to the plus ik dot x. Okay? So again, this guy and this guy integrate over k is phi of x, and then phi of x prime is just the same thing, but now k prime e to the minus ik prime dot x prime plus ak prime dagger e to the ik prime dot x prime acting on the vacuum. Okay? And now you see how it goes. Whenever, the reason why we always use the raising and lowering operators is because once you write it out, you can see very clearly which terms will contribute. Right? In particular, remember that A is the guy that will kill the vacuum. A dagger is the guy that will create one particle. Right? So this guy acting on the right tells you this will go away. Now, same thing here. The logic here is acting on the left. So this guy corresponds to a k dagger acting on 0 dagger, right? And then this guy corresponds to a k acting on 0 dagger. Okay? So this will kill, this guy acting on the left will kill the vacuum, but not this guy. So therefore we can ignore this. So that will simplify the calculation a little bit. And now we see that at this point we have integral over k prime. Maybe I should put an arrow on both just to emphasize it's a 3 momentum, not a 4 momentum. And then 1 over square root 2 ek, 1 over square root 2 ek prime. And then we have the following. Let's pull out the exponentials. E to the minus ik dot x, and then the other guy is e to the I k prime dot x prime. And then what we have is that we have 0, AK, and then AK prime dagger, 0. Okay? But this guy is what we need to manipulate. This guy, let's do it on the side. We can easily manipulate by commuting these guys. So I write it as a commutator, AK prime dagger, and then the second term is not really there, so I need to add that second term, K prime dagger, AK acting on 0. Okay? And again, the reason why we do this is because this term is automatically 0 because it's acting on the vacuum. A is acting on the vacuum. And then this guy, the commutator, is exactly going to give us a delta function. Right? This is going to be 2 pi cubed delta function of K minus K prime, 0, 0, which we always assume is normalized to 1. So this is nothing but the harmonic oscillator of algebra, if you remember. And therefore, what do we have at this point? We have the following. We have the delta function is going to collapse the two integrals into one. So now I can just write it out in full. It's delta 3, d3k over 2 pi cubed. Right? The other guy is cancelled by, and then we set all the k primes to k. Okay? So you got 2ek, and then e to the minus ik. Now k is equal to k prime, so this is just k dot x minus x prime, and then that's it. Okay, and in fact, let's make this a bit more explicit, because the k's here are unshelled, right? It satisfies the dispersion relation. So this is actually e to the minus ie t minus t prime, and then e to the ik dot x minus x prime. Okay? Yeah. I do want to say one thing, which is that the E is even under flip of K. So in fact, in this case, you will discover that I can just switch the sign of K if I want to, and I will discover that the Jacobian here is 1, because I always take an absolute value. 2ek will also remain the same if I flip the sign of k, because this is just square root of k squared plus m squared. The sign of e, again, is the same, but this guy will change sign. Okay. So again, all I've done is the integrand, the integration variable, the integration variable, I switched the sign, but that tells us that these two expressions are equivalent, right? Sometimes it shows, this issue sometimes shows up, and it might be a little bit confusing. But now we're ready to show that this time order product is nothing but that guy, right? So let's do that. And I'm going to erase the okay, so now let's do it. So 0 t phi x prime, we have discovered is 0 step function of t minus t prime of the Whiteman function. Let's put it this way. Step function of t minus t prime, and then the Whiteman function phi x prime 0, okay, and then plus step function of t prime minus t, and actually what you notice is that you don't have to calculate this again. This is nothing but the complex conjugate of this guy. Right? Why? Because remember that linear algebra tells you that if you have bra A, B, cat, and you take a complex conjugate, you get, this cat becomes a bra, and then the bra becomes a cat, and then you need to take the adjoint of AB. So you get B dagger, A dagger. So this will become, in fact, 0, phi x prime, phi x 0, right? Which is exactly that term over there. Yeah, exactly this term over here. But the reason why I write it this way is because we have to answer to this first guy, which is exactly this guy here. And so what we can write down is right away we can write down integral over k, and then step function of t minus t prime times e to the minus I e t minus t prime over 2e e to the I k dot x minus x prime, and then I add the step function t prime minus t plus the complex conjugate of everything here except the step function. Right, so what is that? That is now e to the plus I e t minus t prime over 2ek, and then this will give you a minus, right? And that's why I want to say that, because if you have a minus, well, you can write it that way, minus I k dot x minus x prime. You can write it that way. But you can also put a plus if you want, right? It doesn't matter as we have shown over here. So therefore I can just factor it all out and it will be exactly that. So let me just write it out. Integral over k over 2 pi cubed. And then again I just factor out all the things that are common, e to the I k dot x minus x prime. Again, remember that sign can be arbitrary, the sign of the exponent. So I'm going to set it to be plus, divided by 2ek, which is common to both. And then I can correct the terms. Step function of t minus t prime, e to the minus IE of t minus t prime, and then plus step function of t minus t prime minus t, and then e to the IE t minus t prime. So this, of course, is exactly this guy. So what we have shown, to summarize at this point, is that we have shown that the Feynman-Green's function, which is I times the integral of e to the minus I k dot x minus x prime over k squared minus x squared plus I epsilon, and the I epsilon is crucial here, is in fact, I wrote it down before, but just want to emphasize this again, is the non-interacting vacuum expectation value of the time-ordered product of the quantum fields, phi at x and phi x prime. Okay, so this is very important. And very often in quantum field theory, we work not in position space, but in momentum space. So if I define phi tilde of k and phi tilde of k prime, sometimes we just get sloppy and we just write it this way. This means the Fourier transform of the two-point function. Okay, so there's a definition. And this guy, you can see, you can just read off the Feynman-Green's function, just I over k squared minus m squared plus I epsilon. And this object shows up all the time in relativistic quantum field theory, in the perturbative calculations of Feynman diagrams. This is the key object to all the perturbative calculations. So I want to highlight that. Any questions for me?
Why we change sign of K?
Why we change sign of K? Where?
Last line.
I'm showing you that it's equal, right? Again, let me say it again why, right? Because everybody except this K is even in K, right? Energy is even in K. And the Jacobian, you always take the absolute value, right? So if you can always change your sign of K if you want, but what will happen is that this will pick up a minus sign, right? And that's the only place it will pick up a minus sign. And why that is important, why I'm raising that, is because it shows up over here, right? I wrote down the second term in our Feynman, in our time-ordered product as a complex conjugate of the first term. But because of the complex conjugate, it will pick up a minus sign. It will pick up a minus sign. But because the minus sign, you can flip it back to a plus. In other words, you can basically put either sign, and it's the same thing. And because of that, you can now factor it out as a common factor, and then that will allow you to compare this calculation and this Chronicle integration calculation. And that's why you are able to prove that they are the same thing. Namely, the definition of the Green's function is nothing but giving you the time-ordered product. I should say one more thing before I take a break. So notice that what this does is that it satisfies the Klein-Gordon equation, but with a source on the left-hand side, on the right-hand side, right? So this guy, when you pass it through the K integral, becomes minus K squared plus M squared, right? So this, when you pull out the minus sign, then this gives you minus I. This minus comes from the fact that you have minus K squared plus M squared. Becomes, you will cancel the denominator, leaving you a minus I, and then you will integrate over the K, and this will give you a 4-dimensional delta function of x minus x prime. Okay. So this actually is a Green's function, which is why I call it G and not D. It's a Green's function because on the right-hand side, it's sourced by a delta function. That's exactly what Green's functions do. Okay, so let's take a 10-minute break, and then we will return to talk about why this whole thing is useful. I want to lay out firstly why this is the case, but for the simple case of correlation functions in scalar theory. Okay? So we can get more complicated once we do electrodynamics and fermions and so on. That gets more and more complicated, but let's do it for scalars.
I'm sorry, is that
Yeah.
delta of k plus k prime or minus k prime?
This one, or this one?
Yeah,
This one?
the one of, yeah.
This one? Yeah, because of this delta function, right? K prime prime must be equal to minus k. You agree?
Yeah.
And k prime prime must also be equal to k, right? So therefore, k plus k prime must be 0, which is why the delta function is k plus k prime. Right.
But how about the one over
Which one? This one is wrong. Sorry, yeah, it's plus. Yeah. Yeah, that's why I wanted to work it out, because I didn't want to make a mistake with the sign. Yeah, sorry, this is plus. Okay. So there are a few things I need to explain. So this will also bring us to the quantum the path integral formulation of quantum mechanics and quantum field theory, right? So let's see. So the first thing, let me say the more general statement. So why are we interested? Let's answer this question first. Why are we doing what we do? Right? So the central object that people calculate in QFT is in fact the interacting vacuum time-ordered product correlation function. So phi x1, phi x2, all the way to phi xn, where n can be arbitrary. Okay? That's what you want to calculate. If you can come up with a way to calculate this in a non-perturbative way, give people an exact answer, then you'll be quite famous because it's a hard problem. It's a technically very challenging problem. So what we do, and this is actually what made the pioneers famous, the pioneers like Schwinger and Feynman, so on. These people were famous because they found the perturbative methods to tackle this problem. And so what I want to tell you today is that, let me cut to the chase and tell you that this guy, in fact, the way we tackle it perturbatively is through the path integral. Okay? And so let me write it down and then I'll explain to you how things work. So this guy turns out to be d phi, I'm just going to do scalar theory for now. So phi of x1, phi of x2, all the way to phi of xn, and then e to the I, whatever action that governs the dynamics of phi. So this is a path integral where you integral this, that's why I put a capital D, in case people are not familiar. This tells you, let me just be rough here, because it would take 2 weeks to talk about path integrals just on its own. But basically what's happening is that you're now looking at each point in space and time, and you're looking at all the fields that occur, and you're trying to integrate over all possible field configurations at each possible space-time point. Right? So this guy is actually a very wild object. It's a very wild object, right? But physicists do wild things, so it's okay. We'll, as I'll show you, we'll see how to handle this, at least using perturbation theory, right? So this guy turns out to be a ratio of path integrals. Is this path integral involving this bunch of fields divided by the one without? So it's just e to the I s of phi. That's my claim. Okay, this is a central object that occurs in perturbative quantum field theory. Right? If you at least for this last few weeks, if you forget everything I tell you, at least remember this formula. It's one of the key formulas in QFT, right? And so what we do, in fact, is we often don't tackle this guy exactly. We don't tackle this guy as it is, but in fact we use a trick due to Schwinger. Maybe I shouldn't write equal. So what we do is we use a trick due to Schwinger. And introduce a fictitious J. So a fake source. Okay. Well, fake is my word, but people used to say it's Schwinger's sorcery, right? Sorcery in English means black magic or something like that. But we joke because that's what Schwinger likes to do. He likes to introduce a source. So what do you do? So what you do is the following. Instead of considering this, you consider instead this object, which I'm going to call Z prime. I think Z is usually the partition function, but it's not, what I'm doing is not quite the partition function, so I'm going to call it Z prime. And it's defined to be the following. It's defined to be this ratio, but instead of having a correlator like that, I will introduce a source. So it's e to the I action, and then I'll add to it I times the integral of j of x and phi of x. Okay, actually it can be any dimension I want, so let me just put a d. Okay, and then divided by d phi of y. So I claim that if you know how to handle this object, then all of this, all possible ends are subsumed in this object. Why is that so? Because let's Taylor expand the exponential in powers of j. Right? So if you Taylor expand the exponentials, what will happen is that you go from 0 to infinity, and then let's do it. So you got integral of, if you have L powers of this guy, actually let's put n. If you have n powers of that guy, what happens? You get n, x1, x2, integral all the way to xn of what? Of j x1, j x2, and all the way to j xn. I'm Taylor expanding the exponential here. I to the n divided by n factorial. And then what do we have here? We have in the rest of the expression d phi, and then remember this came from Taylor expanding this. So I will have phi of x1, phi of x2, all the way to phi of xn, e to the is of phi divided by integral d phi e to the is of phi. Okay, again, I'm just Taylor expanding this exponential, and if you write it out explicitly, what you discover is that the coefficient of the nth order term in J is in fact nothing but what I want over there. But now this object, you can see, contains all of them. Give me any n you want, and if I can calculate this object, I will be able to read off for you what the endpoint correlation function is. So in fact, let me just write it down. This is actually n equals to 0 to infinity. ij1, ij2. I'm just going to write it in short form. ij1. J1 means x's. J of x1 all the way to ijn over n factorial. This is again an integral from x of x1 through xn, and this is actually nothing but the interacting vacuum time order product of phi 1 through phi n. Okay. So again, if you know how to compute this z prime, then the time ordered endpoint function can be extracted from this object. So the question is how to deal with this. By the way, so this is not, of course, this is not how Pascal showed it, or towards the end of today, I should explain a little bit more where that formula comes from. Right? So right now, I'm just telling you that it is true, but I didn't tell you why it is true. Why is the time ordered product correlator vacuum expectation value the ratio of these path integrals, right? And you should ask me why, right? And the reason is because of the character of path integration. It's not even it's not even, particularly the time order product part, is not even a quantum field theory statement, but really is a quantum mechanical statement. But because of the lack of time, we are going to, I'm just going to tell you in words what happens. But let's handle the technicalities first, and then I'll tell you about the conceptual one. So what we're going to do is we're going to look at z prime, but now this is going to be a ratio of d phi of exponential of the following I, and then integral over x prime, over x of what? Of 1/2 grad phi squared minus m squared over 2 phi squared. So that's non-interacting Klein-Gordon scalar. But then we have to remember now I want to add a j times phi. Okay? That's what I want to do. So non-interacting case, but now with the j divided by the path integral without the j. Okay? Now, it turns out that because we're integrating over space-time, all of space-time, it turns out to be easier to work in Fourier space-time. Okay? And again, this discussion can be found in Pascal and Schroeder, but in a funny way. What they end up doing, I think they're trying to be very careful. So I certainly appreciate what they're trying to do, but they discretize space-time, and you get a lattice, and then you read the part. They have a kn, and you sum over n, and so on. But essentially, if you are willing to buy what they want to say, is that if you are integrating over space and time, you may as well make use of the symmetries of space-time and go to Fourier space. And what you will discover is that the integral over space-time of 1/2 grad mu phi minus m squared over 2 phi squared at x plus j of x, phi of x, is, in fact, if you just go to Fourier space, you can write it in K space, because, in other words, if you just insert phi of x is dk of phi tilde of k e to the minus I k dot x. Right? If you integrate over all k, both the time and the space component of k, this is just a Fourier transform. And what you discover is that, for example, partial mu will be replaced with minus I k mu. Okay? But there are two of them, okay? And you have an integral over x. So what you will discover is, I'm going to just tell you, and then you can try it out at home if you don't believe me. This guy will turn out to be basically k squared, k mu, and one will be, you can basically write one as phi tilde and the other one as phi tilde star. Okay, so what you will discover is that this will give you k squared, this will give you m squared, and then, like I said, phi here will give you phi tilde of k and phi tilde star of k. Okay, and because it's real, actually, what will happen is the following. If you work it out, you'll discover that this one is minus k and one is k. Okay, but because it's real, you can actually just take out the minus sign and put a star on it. Okay, that's what you'll discover if you work it out in detail, right? So let me just write it down as a footnote. Phi star of k is phi of k because phi is real. Phi in position space is real. Okay? And then this guy, you can write it in different ways, but I can split it up into 1/2 j tilde, j is also real, so j tilde of k, and phi tilde of minus k, and then this guy will be, the other guy will be 1/2 of j tilde star, or this is star, and then this guy will be j star of phi tilde k. Actually, it's the same thing, right? It's the same thing. But I just want to write it out in a symmetric form. Okay? So why do I do this? Because let's look at, for example, the denominator. Okay? So the denominator looks now something like that. So here I'm going to be a little bit sloppy, okay? But let me just write this. So firstly, what does the path integral do? This guy, if you are integrating over space-time, means basically that at every point in space-time, you're doing an ordinary integral over all possible field values at that point. So this is the wild part about path integration, which is that you have an infinite number of ordinary integrations because at each space-time location, you're integrating the field over all possible values, which means you have a continuous infinity, uncountable continuous infinity of ordinary integrations that you have to do over all the field configurations. And moreover, because now I'm going to do it in momentum space, I can also think of this as an integral over all the Fourier components of phi over all Fourier space-time points. But because phi tilde, if this is real, phi tilde will be complex, so I have to now integrate over both the real and the imaginary components, right? So depending on what you want to do, that's what you need to accomplish. You need to look at the field at every point, either in space or in space and Fourier space, real space or Fourier space, and then integrate at each point over all the phis. So it's a pretty wild object, and in general, it's hard to make sense of it, right? But we will be able to handle it perturbatively, as I will show you. So what's important also is to recognize that if you, particularly because we're looking at it in Fourier space, what we are really doing here is that, for example, d phi, the is plus I integral j phi, let's not worry about j phi for now. What's happening here is that, like I said, you're integrating over for all the phi tildes, the real and the imaginary parts. And now that we have managed to write it in terms of Fourier space, what we have is I over 2 integral over k prime squared minus m squared phi tilde whole thing squared. Okay, because phi star is just phi absolute value squared. And what we realize is that basically, because I'm taking every point in k and I'm trying to integrate over all of this, once you see that's what you're doing, you will see why it is useful to do this integral in Fourier space. Because once you do that, you see that actually what's happening here is that this is a sum, this integral is just a sum over k, but this basically means that you can view this integral as basically an infinite product of I over 2, and then k squared minus m squared phi tilde of k squared. Okay, so it's, why do I say this? Because this is a sum. But if you multiply your exponential over all k points, this infinite product will exactly give you the sum over here. Okay, at least heuristically, right? There are problems with what the measure is and so on. But again, the sum over k is basically, you can factorize it out because of the form of this non-interacting actions. You will see that this exponential of the sum is just nothing but a product of the exponentials. And what the path integral means is that you take at each k this exponential, and you now try to integrate over all possible phi's at each k. But then, at each k, you can see this is nothing but a Gaussian integral in complex. This is just Gaussian. Or it's an imaginary, it's a purely imaginary, but still it's a Gaussian. Right? Imaginary because it's I. So this is also why when you do quantum field theory, very often when you say you have a non-interacting theory, when you have a Gaussian theory like this, non-interacting theory, people say you have a Gaussian theory. The easiest way to see that it is Gaussian is to in fact go to Fourier space, because this path integral at each point in k space is in fact an imaginary Gaussian integral. The wild part comes from the fact that you need to multiply this Gaussian integral over all k's. And the question is, what does that become, right? But like I said, we'll be able to handle that, so at least in this case. So don't worry about that. What we do need to worry about is that even in this situation, you see that when you're doing a Gaussian integral, this integral is kind of like doing, let's simplify the problem a little bit, right? Because this is basically this phi tilde squared is just basically the square of the real plus the square of the imaginary part. So we really have two Gaussian integrals, one over the real and one over the imaginary. So we may as well just focus on one of them. So it's basically like doing this minus infinity to plus infinity, e to the minus alpha z, where alpha is real, right? Alpha for us is k squared minus m squared over 2. So this integral, strictly speaking, is actually, I'm sorry, there's a z squared here. This is actually a little ill-defined. As it stands. The reason is because, let's think about what is e to the I alpha z, e to the I alpha z squared. E to the I alpha z squared, if you plot it, either when you go this way or this way, you will discover that when z gets very large, the integrand will oscillate very, very wildly, right? Because this gets very, very large, and this is either when you're looking at the real or the imaginary components, the exponential will oscillate very, very wildly. So this integral on its own is in fact completely ill-defined. How do you handle these guys? It will happen over here as well, right? When you go to either minus infinity or plus infinity. So what you need to do is, even at this point, and even in this integral, the way to regularize the integral is to, instead of doing that, is to displace it slightly. How? You want to make sure that when you go to very large z squared, you want to displace your alpha by I epsilon, where epsilon is again a small infinitesimal positive number. Why? because then this becomes e to the I alpha z squared. This oscillates wildly when z squared is large, but you have a part that damps out minus epsilon z squared. So this part helps to damp out the integrand when you go to very large z, and that makes it well defined, right? So it's a trick, and it's a choice that we make. Otherwise, this integral makes no sense. It doesn't converge, basically. It doesn't converge to a unique answer. So we have to do this even at this level, which means for the path integral, what we end up doing is that we are obliged to shift it by an I epsilon phi to the square. Okay? And what we're going to discover is that this is nothing but a Feynman Green's function. Right? So just by demand that the path integral in Fourier space needs to converge properly. Otherwise, the path integral itself doesn't make sense. It's already wild enough. You're multiplying infinite number of ordinary integrals over k space. So at some point you have to make some sense, right? And so this is why this is what you need to do. You need to shift your Gaussian integral by I epsilon. Otherwise, it will not converge. But once you do that, then we are in business. Okay, and so this is where we need to figure out. Where does that lead us? And it turns out that the rest of the steps is just algebra. And in fact, the rest of the steps, you can see, will just be completing the square. Okay. So let's complete the square. Complete the square in Fourier space. Space-time. Okay, so what do I mean by that? So the action we have discovered is k, and then 1/2 of k squared minus m squared, and then now we realize we need to add an I epsilon, and then phi tilde squared, and then we have to remember there's a 1/2 j tilde star, phi tilde, and then plus 1/2 j tilde phi star. Okay, actually you can just combine them to one object, but I'm just doing this to make it look symmetric. But now, complete the square means the following. Let's try the following, right? So what do you do when you complete the square? You're basically shifting phi by a constant. So I'm going to replace phi with little phi plus a phi independent object, which I'm going to call g tilde. Actually, let me do I g tilde and then j tilde. So all of this will depend on k, right? So this is phi of k, this is little phi of k, script phi, little phi, this is gk, and this is jk, okay? And now, let's just plug it in, right? So what do you get? You get that now s is the integral over k, 1/2, actually there's a 1/2 everywhere, so I'm going to just write 1/2 outside. Integral of k, and what you have is you get k squared minus m squared plus I epsilon, and then what you have is you get the square of this guy, so you get a bunch of cross terms, right? So let's do it. So you get phi tilde squared, you get the square of this guy, so g tilde squared, j tilde squared, okay? That's this guy, and then the cross terms. Right, remember the cross terms come from taking this conjugate times this, plus this conjugate times this. Okay, so it's phi tilde star times I G tilde J tilde plus the conjugate of that. So you get minus I G tilde star and then J tilde star times phi tilde. Okay? And then we have these guys. 1 plus what time is it? Oh no, okay. So let me just write it out and then we'll see, we need to go a little bit further. J tilde star, and then phi is now little phi plus I G tilde J tilde, and then plus J, and then phi star is little phi tilde plus minus I G tilde star J, yeah, that's right, star. Okay. Okay, so maybe for the lack of time, let me tell you the answer. Okay, but the point is the following. The point is to complete the square so that phi, little phi, will just show up on its own. Okay, and this can be accomplished if you choose G tilde appropriately. So let me just cut to the chase. So if you choose G tilde to be I over K squared minus M squared plus I epsilon. What it means is basically is I times the inverse of this kinetic term. Remember, this comes from the kinetic energy, which is this part. So in position space, this would correspond to choosing G tilde to be actually the Feynman-Green's function. Okay, and in fact, this is the Feynman-Green's function, but in Fourier space. So you can see that completing the square naturally will lead you to the Feynman-Green's function. If your goal is to isolate phi, okay, then what you will discover is the following. You will discover that your action will now be 1/2 integral over k, and then you get k squared minus m squared plus I epsilon, and then it will be little phi squared, and then you will get minus j tilde k of that's right, of 1 over k squared minus m squared plus I epsilon j tilde star. And in fact, this minus sign, I'm going to write it as plus I, and then I'm going to put an I here. That's right. So that is exactly what we mean by completing the square, right? I rearrange this action that used to have phi tilde, and then you had phi interacting with j, but now when I rescale it like that by a shift, then I managed to write phi tilde on its own, and then you have jj. Okay, and so what does it look like now? And then let me just write that down, and then you can see what's happening. So what happens to z prime is now, it looks like the following. Z prime in the numerator is d phi, and then the exponential of two terms. One is I over 2 integral over k of k squared minus m squared plus I epsilon of phi, phi tilde squared. So I should say, this integration variable is a dummy variable, right? So if I shift it by something that doesn't depend on phi, d phi is equal to d little phi, because this guy doesn't depend on phi. So it's just like ordinary integration, where when you shift it by a constant, the measure of the integral doesn't change, right? And since it's a dummy variable, I'm going to use back my phi. Now, there's an additional term here involving this guy, so I'm going to write it down as the following, right? This is also times exponential of I. Now if I go back to Fourier space, position space, you'll recognize that this is actually the Feynman-Green's function, and this will be I times the following. There's a 1/2 out here, so it will be I over 2, and then it will be integral over x prime and x double prime, j of x, Feynman-Green's function of x minus x prime, j of x prime. The whole thing divided by the path integral without the j. So what is that? That's just the same, the numerator without the j, which is just d phi exponential of I over 2 integral over k prime squared minus m squared plus I epsilon phi tilde squared. So now you see why we don't have to worry about path integrals that much. Even though it's a wild object, the fact that we have a ratio of path integrals tells you the wild part, which is this integral over, all these field configurations. Well, they cancel out. They cancel out. The only thing that remains is the exponential of this fictitious source, j, integrated against my Feynman-Green's function. Okay? And so all that remains is that z prime, and this is the main formula for today, z prime in the non-interacting case, or the Gaussian case, or the free theory case, free Klein-Gordon or Gaussian theory, right? This is just jargon, but these are jargon that you see a lot in field theory literature. Is in fact just the exponential of I over 2 integral over x prime prime, j of x prime, Feynman-Green's function x prime minus x prime prime, of j of x prime prime, right? That is the key, this is the key formula. And what we'll discover is that when you introduce interactions, you will discover that the interactions can be written in terms of derivatives of this object. Okay, and I'll explain that next time. But once you realize that, then you'll see that that's why the Feynman-Green's function is the core of all of perturbation theory in QFT. Any questions?
So the physical meaning of the Green function is related to the interaction between the source.
At this point, it's really just a trick. If you're asking, does it mean something, right? So right now, you should just think of it as a trick that I use to generate, that's why it's called the generating function. It's a generating function because if you remember, maybe half an hour ago, I